This video is about a light interference experiment. We're going to show you how to do it. This experiment rejects all wave models of light and all wave particle duality models. The idealism of science is that a valid experiment trumps any model. So here we have an experiment which is repeatable. I'm doing this so that an amateur scientist can do this experiment on his own and see for himself the results. Light interference is at the heart of quantum mechanics. If we have a particle model of light that can produce interference, then we question the quantum mechanics. So this is the experiment. This is just a laser pointer, which is easily available to even amateurs. It's directing its laser beam onto a slit. This is a single slit. It's made out of, here's a business card. We put a hole in the business card and a piece of aluminum foil with a cut in it. The cut is about 1/2 millimeter wide, and you can see the light coming through the slit. Now this produces a diffraction pattern. And there you see the diffraction pattern projected on a white background, which is about 8 meters away. This is the screen image from the light through the first slit onto the screen, which you saw was 8 meters away. This is a normal diffraction pattern. The laser beam is directed onto a second mask. The second mask consists of glass plates. This is just normal window pane glass. And you see here the direct diffraction pattern goes through the glass. Now, this part of the experiment is known as the Hodge experiment, which was explored in an earlier video. This is experiment B, where we put a piece of glass between the first slit and the screen. The glass is transmitting the image fairly well. Now we direct the laser beam and this diffraction pattern through a very narrow slit, about 1/2 millimeter across, between two pieces of glass. You'll see there's the diffraction pattern. This is the third experiment where we put the slit over the center of the diffraction pattern. And you see what you get here, if you can see these little lines here, those are interference fringes in all the various sections of the diffraction pattern. And here's an expanded view of this area in here. We put a nail in the path of the light, and you can see that the center portion of the light here of the diffraction pattern is totally on the nail. That's to say, the first minima are on each side of the nail. That the light from the center portion, that is to say, the light that was going through the slit, is no longer going through the slit, as you can see here. But yet, there's no light going through the slit, but yet the interference pattern remains. And here you see where we put the nail in. The nail is right, this is the shadow of the nail. There's a couple things to notice. One is the diffraction pattern is intact. These are interference fringes, and they are still there when the center of the image is blocked. Another thing I'll note is you see a very faint piece of light right there and right there. And the nail shadow is right in here. So there's no light coming in where the nail is, where the center peak used to be, and we still have interference fringes without light going through the slit. This is the basic Hodge experiment. We had a laser, and we had a single slit screen or mask here, which then let through, and if you remember what this was a regular diffraction pattern that fit the Fraunhofer equation, and then 8 meters away we had the screen. And of course that paper. This comes from that paper. This is a computer toy simulation of the image onto the second mask. That is to say, it's the image from the first mask that's projecting onto the glass plates. This is a regular Fraunhofer type diffraction pattern, which is expected by traditional physics. We put the edge of the glass slit right there and right there, so this part goes through the glass slit. Now, you'll note that that is not uniform distribution across the slit. That's part of the Hodge simulation. The other thing you'll note is some of the light here is impinging still on the glass by the side of the slit. I remarked on that. The blocking nail edges are at the minima of the diffraction image. No light through the slit. Now let's see that. This is the edge of a mask, and here we position the edge right in the middle of the diffraction pattern. The image on the screen of this kind of setup is like this. So here you can see the diffraction pattern on that side, but there's the center of the image. This comes through, but more importantly for this experiment, a lot of light comes through behind the mask. Now, traditional physics explains this. But this is what happens when you put the edge of a blocking mask at the minima of a diffraction pattern. What you see here, and it's kind of hard to follow this down, but still there's a very small amount of light that comes right just inside the mask here, and then the rest of the diffraction pattern follows. The point is that where the center peak used to be, there's no light. This is the simulation of the present experiment, and this then is image C that we saw before. So here you see the peak, here you see the secondary maxima and minima. Now, what we're going to look at next is this part of this image, just to show you these little squiggles, what they are. And this is it. This then is the big peak over here. That's the first minima. And then this is that diffraction pattern. But inside the diffraction pattern, there are these zeros here, which represent interference fringes. So you see the simulation is duplicating the interference fringes and therefore the diffraction pattern. Traditional science requires light to pass through slits in order to form the interference pattern. This experiment places the slits one in front of the other, but we still have a diffraction image, and we still have a second slit that is causing the diffraction pattern to go through an interference pattern. The second introduces the interference friction. This is then a double slit experiment, just not what you usually think of as one. Now, the light from the center of the first slit is blocked. And we saw by putting that edge of the slit at the minima, all the light is blocked. There's no light going through the slit. Therefore, the remainder of the first slit diffraction pattern passes through the glass and is coherent. So you can see this video for a discussion on what coherence is. The resulting interference pattern is not formed by the interference of light through the second mask slit. And of course, the light going through the glass isn't changed either. So therefore, the mere presence of a slit must form the interference pattern. Now, traditional science cannot explain this, and wave models of light don't explain this. The Stowe model suggests the diffraction images, you can see the reference video, and the interference images are formed by reflecting the plenum waves, which direct the photon's path, just like in general relativity. The lack of a reflecting surface in the gap means the remaining part of the mass directs the photons onto the interface pattern on the screen. Light diffraction and interference is at the heart of quantum mechanics. But here we've rejected the wave part of quantum mechanics.
Here are a few other papers I've written. Note that when a photon pulse is emitted from an atom or absorbed, the electron undergoes a level change and a photon is emitted or absorbed. That's the current model. I interpret this as indicating that photons are part of the structure of the atoms, rather than the electron absorbs or emits the photon. So here then is the atomic structure of the atoms. Here we see electrons being held in place by photons. These go to the nucleus, and these are held next to each other. And of course, those going out are going to other electrons, or they're just free. You'll note that when you take this assembly of electrons and kind of shake it a little bit, what you get is a small little angle right in here. And this angle has two bounds. One, in terms of making a circle of these electrons, produces 8 electrons in a circle, and the other produces 18 electrons in a circle. These are magic numbers in atomic structure. And this is how you form an ionic bond. With the magnetic attractions here, you have a place where an electron might be in the structure, but isn't. And so here's another electron attached to another atom out this way, and you can see that it can fit right in here. You will also note that there's a lot of magnetic force here, here, and here, and this creates a potential magnetic force here, which the semiconductor folks call a hole. This is how you have hole conduction. You'll note that gravity, that is to say, the gradient of the plenum, has an effect on the surface area of the HOD. But if you remember what a photon looks like, you'll see that a photon only has a surface, just one type of surface, and that force then is directed along the axis of the photon and not in the direction of movement. The direction perpendicular to the plane in the center of the photon has the force equal to 0. The neutrino structure had 2 axes, and therefore the force along one of these axes is, as you see here, not the full force. A 3-dimensional body, such an electron, has the force being able to be produced in 3 different directions, and therefore it is a smaller force than is on HODs. So there's different types of forces, and this produces some interesting phenomenon. Note an interesting thing about magnets. If you have a north-south magnet, another magnet is going to be attracted either slightly to the left or slightly to the right. These are little balls, and what we're doing is proposing, following Emmanuel's, who I mentioned earlier, suggestion that nucleons, that is to say protons and neutrons, are spheres of balls of magnets. And each of these magnets on the surface has its axial magnetic force tangent to the ball. So therefore, the magnetic attraction is inverse cubed radially. And of course, it attracts all other magnets, either north or south. And this then is what the Stowe proposes is the strong and weak nuclear forces. That is to say, we now have all the gut forces, strong and weak nuclear forces, gravity, and the magnetic and electric forces. This then is what a nucleus might look like. Several balls like this all lined up. Now, the interesting thing about this structure is that if you have these two balls of magnets like that, there's an extra force here at the opposite end of where this is that attracts photons. And you'll see that if there's other photons coming out from here, such as here, they are directed back to be in more or less the actual direction of this structure. And this kind of a structure, where it goes in a loop, isn't allowed. It's prohibited. So here you have a single photon structure that ends up being the attachment to an electron. One electron per one proton. The Stowe has made several predictions that we have covered. The interference of light in the transparent mass experiment was actually predicted, meaning I was looking for that kind of a thing. I had tried several other experiments trying to show the model worked, and there was someone who I was in communication with at the time, a Dr. Sato, and he was always able to come up with an additional assumption that you could make to the wave model that would fit my experiments. But that really led to not only Fraunhofer's 5 weird assumptions, but many more types of assumptions. Well, I guess that's what physics do. But in this transparent mass experiment, that's when Dr. Sato quit trying to figure out how it worked. The Hodge apparatus, which is a laser with a single slit, produces a diffraction pattern with a very well-known distribution, that is to say the Fraunhofer distribution. Now, one of the problems you might run into if you're going to do these experiments is pen lasers, and I've looked at several, produce slightly different types of dots. That is to say, they have optics in them that produce these dots, and these dots may have a structure. The difficulty with this is it's really kind of an unknown structure, and it produces some weird effects sometimes, especially if you're going to use very narrow slits. Very narrow slits will do what's called resolve the image. So this is some experimental issue that you kind of have to watch out for. The maybe, I started noticing the Maxwell's equations differ from the Stowe. The experiment rejected the Biot-Savart law was done because the EM radio signals travel at the speed of light, which implies odds are the elements. However, this seemed to conflict with the Biot-Savart law. So the typical experiment was done using a magnet rather than a parallel wire. The result of the experiment suggested in the Stowe another experiment on electromagnetics, which showed 2 different types of magnetic field and that Maxwell's equation should be redone. Well, I guess we're near the end of the time here. And the Stowe model also looked at cosmology models, but perhaps that could be an issue for another time.